everybody. The chapter is known as generating lines, but over here we are actually discussing a kind of surface known as ruled surfaces. And this what is this ruled surface? Uh, Over here, you see the actual definition of ruled surface is that we shall have to consider the surfaces which are generated by moving straight lines. That means, for example, you see, you can consider a cone or a cylinder. These are obtained by the movement of a straight line. Okay, this kind of surfaces are actually called uh, ruled surfaces. But there are other surfaces as well which are generated by straight lines. We shall mainly discuss this type of surfaces. Mainly, this kind of ruled surfaces are categorized into two categories. One is known as developable surface, another is known as skew surface. And the straight lines generating these surfaces, these are called the generators of that surface. Okay. For example, you see we have discussed cylinders. In cylinders, we had the concept of generators, and apart from cylinders, there are other surfaces as well. So what we find is that there may actually these straight lines should move, and the movement of these straight lines is generating a surface in three-dimensional space. Now, the first category of surface is the developable surface. What is this? Whenever two consecutive generators are intersecting each other. For example, let me draw the picture over here. We are discussing this type of cone. All right, maybe this is a section of the cone. All right, and you see these straight lines, this type of straight lines, these are actually generators. So if you consider two consecutive straight lines, this is maybe one straight line and the immediate next generator might be like this. So all these generators over here will intersect each other at this point. So this type of surfaces are actually examples of developable surfaces. Okay. Over here, this type of surfaces are examples of developable surfaces. And there is one more category of surface, and that is called skew surface. What is this? Now, in this type of surfaces, the consecutive generators would not intersect at all. The consecutive generators would not intersect at all. And the examples of such surfaces are hyperboloid of one sheet and hyperbolic paraboloids. These are the examples of surfaces. Now you may ask, how do we get this type of surfaces, hyperboloid of one sheet or hyperbolic paraboloid? I am showing you an example. You see over here in this type of picture, you can check that this is the example. This is x square by 4 plus y square by 9 minus z square by 16 is equal to 1. This is an example of hyperboloid of one sheet. And if we draw this picture, this would be the picture of hyperboloid of one sheet. You can check this picture from different orientations. And I have drawn a straight line. You see over here from this orientation, you can check over here. I have drawn a straight line, and this straight line, if you can check, if you extend this straight line will always lie on the surface. Now the question is that how do we obtain this type of straight lines? Actually, if we change this straight line, this straight line, if you change this straight line, uh, then one can prove that we can easily change this straight line along different positions of this hyperboloid of one sheet. So this straight line, this straight line would be actually a generator of this hyperboloid of one sheet. Now the question is that how can we obtain the equation of this type of generators? If we draw the picture of hyperboloid of one sheet in two-dimensional plane, it looks like this, something like this type of pictures. And there we have this type of sections. Okay, and over here also we have sections, something like this. The back side may look like this. Now hyperbola of one sheet, these are actually generated by this type of straight lines. If we can check that these straight lines will move along the surface, and it will generate the surface. Now the question is that how can we generate these surfaces? I am coming to this topic. In fact, this is the main topic of this chapter. But before that, I need one result related to this surfaces. Now one can prove this result. Let me show you this result from the book. Where is this? This is the book. Over here, we got the definition of ruled surfaces and skew surfaces, developable surface, etc. Now this is the first result that we shall discuss today. It says that if a straight line meets a conicoid, that means it may be a sphere, it may be a conic, it may be a cylinder, it may be developable surface, it may be skew surface, whatever surface it is. So if a straight line meets a conicoid in 3 points, all right, 3 different points. In general, what happens? In general, a straight line always meets a conicoid in 2 points. But over here, it says that if a straight line meets a conicoid in 3 different distinct, of course, 3 distinct points, then the straight line lies wholly or entirely. Then the straight line lies entirely on the conicoid. All right. Now you see, what is the example? What would be the equation of a conicoid in three-dimensional space? An equation of a conicoid. You can check that equation of a conicoid in three-dimensional space. This equation can be written in this fashion. Say ax square plus by square plus c z square plus twice f yz plus twice g zx, say, plus twice h xy. This is the purely second degree expression, plus twice ux plus twice vy plus twice wz plus g is equal to 0. This type of equation. All right. Now in this type of equation, if you consider the equation of a straight line passing through the point alpha, beta, gamma, in that case, what you observe, if this ratio is taken to as equal to r, in that case compare this first ratio and this last expression R. Then what you get? You get x is equal to alpha plus R into L. If you compare the second ratio with the last value R, then we will get y is equal to beta plus R into M. And if you compare the third ratio with this R, in that case you will get Z is equal to gamma plus R into N. Alright, so you can say that any point xyz, any point xyz lying on this type of straight line will have this x coordinates as x is equal to alpha plus Rn, y is equal to beta plus Rn, and z is equal to gamma plus Rn. So if in this equation, if we put x is equal to alpha plus R into L, and we put y is equal to beta plus Rm, and we put z is equal to gamma plus Rn, then what happens in this equation? Okay, in this equation we are putting these values. I have this benefit that I can replace these expressions over here. This is x, then this is our x, this is also x, and this expression is also equal to x. Let me write it in the next line. This one, this expression is also equal to x. Then what is y is equal to beta plus Rn. So let me write this expression of y. This is y, then this term is y, this is y, then this value is equal to, this value would be is equal to y. And what about z? Z is equal to gamma plus Rn, so this expression is equal to z. Then what we have, this is the expression of z. Again, this is the expression of z, and finally this over here. So this would be the expression of z. Now if we expand this expression, what would you get? If you expand this expression, you observe that you will get a second degree equation in this quantity small r. You will get this type of expression, something like this: a into r square plus b into r plus maybe capital C is equal to 0. You will get a second degree equation involving small r. Alright. Now what we have, we are given that this straight line, this straight line intersects a conicoid. This straight line intersects a conicoid, and equation of that conicoid is this type of equation. But over here what we find? We find that we get a second degree equation in R. Therefore, if we solve this equation, if it is possible to solve this equation, I don't know. If we solve this equation, in that case we would get maximum 2 values of R. This is a second degree equation. We will get maximum 2 values of R. But as per the construction, we were supposed to get 3 values of R, because it says that we should get 3 points. Alright, so it is given that we should get 3 points, and these 3 values of R will actually refer to these 3 points. Okay, so we expect that in this equation we should have 3 values of R, but this would be possible only when, in fact, this equation, if it is satisfied for 3 values of R, in that case it would be satisfied for more than 3 values of r. For all values of r, it would be satisfied, and that would be possible if this capital A, the coefficient of r square, becomes is equal to 0, this capital B becomes is equal to 0, and this capital C becomes is equal to 0. Okay, so if this equation has three solutions, then it is obvious that A, B and C would be equal to 0. And if A, B and C are is equal to 0, in that case you can check that the left hand side will always be is equal to 0. That means we can say that this equation is satisfied for all values of r. And if it is satisfied for all values of r, then each and every point x, y and z must satisfy this equation. Okay, each and every point x, y and z given by this type of expression must satisfy this equation, or in other words you can say all the points x, y and z given by this type of expression, these are actually the points on the straight line. So all the points actually lying on this surface, this is the surface, and this is the equation of a straight line. This is actually the parametric equation of a straight line. Okay, so this all the points x, y, z in this parametric equation, they will always satisfy this equation, or in other words you can say that this straight line given by this type of parametric expression will always lie on this kind of three-dimensional surface or conicoid. This is the final conclusion that says that if a straight line meets the conic in 3 points, then the straight line lies entirely on this conicoid. Okay, then the straight line lies entirely on this conicoid. So this is actually a very short objective type of question of 2 or 3 marks that can be selected in your examination. Alright, so let me continue to the next portion that says what are the skew surfaces that we should discuss over here. Actually there are a few results. Depending on this result what I have proved over here, one can prove this result that hyperboloid of one sheet is the only central conicoid which can be a ruled surface. Okay, hyperboloid of one sheet is only central conicoid. There are many type of central conicoid like ellipsoid, hyperboloid of two sheets, etc. But hyperboloid of one sheet is the only central conicoid which would be a ruled surface or skew surface. And in the similar fashion, one can prove that hyperbolic paraboloid, this hyperbolic paraboloid, this is the only non-central conicoid. This hyperbolic paraboloid is the only non-central conicoid which would be a ruled surface. I am not going to discuss all these results because this deduction of all these results would not be important for your examination purpose. What I am going to discuss is the technique by which we can find the equation of a generator of hyperboloid of one sheet and elliptic hyperboloid. Okay, and we have 4 properties of these generators. So we shall study those properties, and in this class I shall study the properties of the generators for hyperboloid of one sheet, and similar properties are there for the generators of hyperbolic paraboloid. I shall leave the proof of those properties for you. I shall not discuss those properties in this class. That would be your assignment or job, whatever you call, to go through those properties for for this hyperbolic paraboloid. Okay, so let me show you the case over here. You see over here, this is the equation of hyperbolic paraboloid. Let me show you over here. The equation of hyperbolic paraboloid can be written as this type of equation: x square by a square plus y square by b square minus z square by c square is equal to 1, and this expression can be converted into this type of expression: x square by a square minus z square by c square, that is equal to 1 minus y square by b square. This type of expression, and both sides, these are in the form of a square minus b square, so both of these two sides can be written as x by a plus z by c into x by a minus z by c, that is equal to, the right hand side can be written as 1 plus y by b into 1 minus y by b. So this is the equation of the paraboloid of one sheet. Now you see, from this equation we can construct the equation of a straight line. In fact, we can construct the equation of two straight lines. Let me first show you the technique. You see, we can combine this first factor with this factor, and we can combine this second factor with this second factor. How? We can write x by a plus z by c, that is equal to this first factor 1 plus y by b, and this second factor x by a minus z by c, this can be written as equal to 1 minus y by b is 2. So you see, this is a plane and this is another plane, and you can check both of these two planes are not exactly same planes, so they should intersect, and there both of these two collectively will represent a straight line, and any point on this straight line, if you multiply these two equations, you will get this equation number 1. Let me call it this as the equation number 2. Okay, if you consider any point on this straight line number 2, in that case you see, if you multiply left hand side and right hand side of these two equations, you will be able to construct this equation. That means the point would also satisfy this equation number 1. So we can say that the point is actually a point on this hyperboloid of one sheet. Even if you consider a parameter lambda, like this, in that case also both of these two are actually representing two planes, and these two planes will together construct a straight line. So this would be one generator, and this straight line would be the equation of that generator. Okay, this is the equation of a generator, and for different values of lambda we will get different generators, and that's why this is called lambda system of generators. Lambda system of generators. And there is one more generator, there is one more system of generators. How? You see, what we considered, we actually considered this first factor with this first factor, and the second factor with this second factor. Now consider the opposite type of grouping. If you consider this first factor with this second factor, then what would you get? X by a plus z by c. X by a plus z by c, that is equal to what we get, with this positive symbol we get this negative symbol. So we shall write 1 minus y by b. And with this x by a minus z by c, we will have 1 plus y by b. This type of equations. Even you can check that you can consider a mu over here, and this is 1 by mu over here. So this would be another set of generator. Let us call it equation number 3. And one can also prove that this system and this system, these are actually two different systems, and this system is called the mu system of generator. Mu system of generator. Okay, this is called the mu system of generator. In fact, in some books, it is also in place of mu they have written 1 by mu, and in place of 1 by mu they have written mu. So you can also write it in this fashion. In fact, in the textbook what I am discussing, there also they have discussed this type of expression. So over here this is our mu and this is our 1 by mu. It doesn't matter. Similarly over here in this book, over here in this book they have written this is our lambda, and over here 1 by lambda. It doesn't matter. Now the question is that the properties of these generators, they say that that any two consecutive, this is the first property that I am going to state, the property number 1. Property number 1, I shall discuss this property. It says that any two members intersect each other. Any two members of lambda system will never intersect each other. Similarly, any two members of this mu system would never intersect each other. This is one property, and that's why this type of surfaces are called skew surfaces. I told you that two consecutive generators would never intersect each other. So these properties can, the proof of these properties can be given as a question of 3 to 4 marks. So I am going to discuss this property over here. You see, let me consider this lambda system of the hyperboloid of one sheet. What was the hyperboloid of one sheet? This was the equation x square by a square plus y square by b square minus z square by c square is equal to 1. And the lambda system was taken to be is equal to x by a minus z by c, that is equal to lambda into 1 minus y by b. And the second equation was x by a minus plus z by c, that would be is equal to 1 by lambda into 1 plus y by b. This was the lambda system. Now suppose we consider two members from this system. How do you obtain two members? One, you can say for lambda is equal to lambda 1. Another, you can say, you can consider for lambda is equal to lambda 2. So if we put lambda is equal to lambda 1 over here, you will get one generator. Let us call it let us call this equation as the equation number 1, and let us call this generator as equation number 2. So if for lambda is equal to lambda 1, you get this generator. Again, for lambda is equal to lambda 2, you will get another generator like this, x by a minus z by c, that is equal to lambda 2 into 1 minus y by b. and the second equation of that straight line would be x by a plus z by c, that is equal to 1 by lambda 2 into 1 plus y by b. So let us call this relation as relation number 3. Okay, so this is another generator. Now you see, we can, if it is possible, we are going to show that this equation number 2 and 3 would never intersect. We are going to show that whatever value of lambda 1 and lambda 2 are, this equation number 2 and 3 would never intersect. And of course, over here, lambda 1 is not equal to lambda 2, otherwise both of these two equations will coincide with each other. So if lambda 1 is lambda 2, lambda 1 is not equal to lambda 2, then we are going to prove that 2 and 3 will never intersect at all. Okay. Now, how to find out the intersection? If there is any such intersection at all, we will try to solve this 4 equation. This is one equation, this is equation number 2, this is equation number 3, and this is equation number 4. We shall try to solve all these 4 equations. How can we solve this equation? Let us try to first consider this first equation and this third equation. Okay. This is the equation we are considering, and this is the equation we are considering. Now, if we compare both the left hand side of these two equations, what we will get, that this right hand side must be equal to this right hand side, or in other words, we will get this type of result, that lambda 1 into 1 minus y by b, y by b, that is equal to lambda 2 into 1 minus y by b. So you can write this expression as lambda 1 minus lambda 2 into 1 minus y by b, that is equal to 0. Now you see, lambda 1 is not equal to lambda 2. We have already taken this result. So it means that lambda 1 minus lambda 2, this would be not equal to 0. And if this factor is not equal to 0, then what is the possible case? The only possible case is that we can cancel these factors. We can cancel this factor, and only possible case is that this second factor 1 minus y by b is equal to 0. And it means this is, therefore the only solution is y is equal to b. So we get a result y is equal to b. Let us mark it as equation number 4. Now over here, let us now consider this second equation, second set of equations, this set of equation, this equation and this equation. Now in this second set of equation, this left hand side is equal to x by a plus z by c, and the right hand side is also x by a plus z by c. So we can compare these two right hand sides. Then comparing these two right hand sides, what we get? We get this type of result, that 1 by lambda 1 into 1 plus y by b, that is equal to 1 by lambda 2 into 1 plus y by b. So from these two results, we get that 1 by lambda 1 minus 1 by lambda 2, both of these two multiplied by 1 plus y by b, this is equal to 0. Now we are given that lambda 1 is not equal to lambda 2. Now as because lambda 1 is not equal to lambda 2, therefore we can say that 1 by lambda 1 is not equal to 1 by lambda 2. And this should imply that this factor, this first factor 1 by lambda 1 minus 1 by lambda 2, this first factor is not equal to 0. So what result we get from this relation? The only possible result is that this 1 plus y by b, this factor would be equal to 0. 1 plus y by b would be is equal to 0, and this means that y is equal to minus b. Okay, let us call it relation number 5. Now what you observe is that once we get y is equal to minus b in this relation number 5, and in this relation number 4 we get y is equal to plus b. So this is a contradiction. B is not equal to 0. We know that B is a positive quantity on the length of one semi-axis. So B is not equal to 0. But if B is not equal to 0, then Y is equal to plus B and Y is equal to minus B. Both of these two cannot simultaneously be true. So this is possible. Why we are getting this type of opposite results? Because of our wrong assumption. What was our assumption? We were actually trying to solve this equation number 2 and this equation number 3. We were trying to solve and find whether there is any point of intersection at all. But in order to do this result, we get some contradictory result. So this contradiction says that we cannot ever find out the point of intersection of this lambda of this system with lambda is equal to lambda 1 and of the generator with lambda is equal to lambda 2. So we can say that two generators in the lambda system, they can never intersect. Okay, two generators in the lambda system, two generators in the lambda system, they would never intersect. All right, two generators in this lambda system, they would never intersect. Similarly, if we consider mu system, you can prove that any two generators in the mu system will never intersect. All right. Now see, is this much clear to you? Hello?
Yes, sir.
Yes.
Yes. Okay. So let's try to prove the second property. You see, what is the second property? The second property says that if we consider this was the first property. This was the first property in your book. No two generators of the same system will intersect. And what is the second property? The second property, I am proving this second property from this book. The second property says that two generators of different system, that means one is taken from lambda system and one is taken from mu system, they would intersect. And over here we shall also find the point of intersection. So this is one system, the lambda system of generator. Another is this mu system. This is the mu system of generator. Now we are trying to solve these four equations and check whether there is any such point of intersection or not. So what we are doing, we are actually in this case from this first equation, from this one, from this first equation and from this third equation, we are considering these two equations. From this equation number 1 and this equation number 3, what we get, if we compare these two results, we will get that this right hand side, you see on the left hand side we actually have x by a minus z by c, and this one also x by a minus z by c. So in this over here, this expression, this right hand side expression must be is equal to this right hand side expression. So we are comparing these two equations, we get this result. Now you see the only variable term is y. This is y, this is y. So we can make the mathematical manipulation and ultimately we will be able to find out the value of y. So what would be y? If we shift this b on the right hand side over here, in that case we will get this expression of y. Fine. Now again, if you consider this equation number 2 and this equation number 4, you see in equation number 2 and equation number 4 we have the expression of y by b, this one as well as this one. So over here we can put this expression of y by b is equal to this type of expression lambda minus mu divided by lambda plus mu. So if we put these expressions in these two relations, we will have this type of relation. This is the first result that would come out of this equation number 2. And what would be the second result? This is the second result. This is the second result that would come out of this equation number 4. Okay. Now what we have, you see the expressions on the left hand side. This is x by a minus z by c. This is x by a plus z by c. So if you just simply add these two equations, these two results, you will get the expression of x by a. This z by c and this z by c will get cancelled. So you will get the expression of x by a, and that would be the expression of x by a. X by a would be this type of expression. And again, if you subtract these two equations, in that case this x by a and this x by a will get cancelled. Only we shall have the expression of z by c. So this would be the expression of z by c. So in this way, we can find out the expression of x by a, y by b, and z by c. So this y, if you shift this b over here, you will get the expression of y. Similarly, if you shift a over here, you will get the expression of this x. And similarly, if we shift this c over here, you will get the expression of z. So we are getting certain expressions of x, y, and z like this. This is the expression of x, this is expression of y, this is the expression of z. So what we are getting, we can say that yes, we get actually the point of intersection of two generators. One generator is taken from lambda system, another generator is taken from the mu system. Okay, therefore we can say yes, these two straight lines will intersect each other. In fact, if you in this equation, if you simply put certain definite value of mu, suppose mu is equal to 1, then you will be able to get the parametric equation of lambda system of generator. You will get the first coordinate would be written in terms of lambda, the second one, and similarly the third one would be written in terms of lambda. Similarly, if you put certain value of lambda over here, say lambda is equal to 2, you will get an expression involving mu. This would be the x coordinate, this would be the y coordinate, and this would be a z coordinate involving mu. So you will get a parametric form of the mu system of generators. And by the help of this expression, I have drawn this picture over here. You see, actually this is the parametric form, and I have put over here lambda is equal to 1. So by putting lambda is equal to 1, I am actually drawing the picture of this generating line. Okay, so over here in this way we can prove that these two generators are intersecting each other. Okay, and the third and fourth result, one can easily prove this result, that whatever point on this hyperboloid of one sheet you consider, from each and every point, whatever point of hyperboloid of one sheet you consider, you can draw one generator from lambda system and another generator from mu system passing through this point. Okay, this would be a generator from lambda system, this may be the generator from lambda system, and this may be the generator from mu system. So through each and every point you will be able to draw this type of generator. How to prove this result is easy proof. You see, suppose alpha, beta, gamma is a point on the hyperboloid, so it must satisfy the equation of the hyperboloid of one sheet. So just by putting x is equal to alpha, y is equal to beta, and z is equal to gamma, we get this type of result. And again, you can make this type of manipulation over here. You see the kind of manipulation I did in this example in the previous system. Just in place of x, we can put alpha. In place of y, we can put beta, and in place of z, we can put gamma. So let me show you over here. Say we will have this type of expression quickly: x square by alpha square by a square plus beta square by b square minus gamma square by c square is equal to 1. So what we will get, this will be is equal to alpha square by a square minus gamma square by c square, that is equal to 1 minus beta square by b square. So this expression can be written as alpha by a plus gamma by c multiplied by alpha by a minus gamma by c is equal to 1 minus, or you can consider the plus symbol over here, beta by b, this is one factor, and then 1 minus beta by b, that would be the another factor. Now you see this expression can be arranged in this way. It can be arranged in two different ways. One is this one, alpha by a plus gamma by c, this is one factor. This is divided by, say, the positive factor 1 plus beta by b. Okay, this is the positive factor, that is equal to, let's combine these two negative factors over here, 1 minus beta by b divided by alpha by a minus gamma by c. So if you consider this expression to be is equal to, say, lambda, then comparing this first ratio with lambda, you will get one equation, and comparing the second ratio with lambda, you will get another equation of involving alpha and beta. Similarly, you can consider the second system just like this, alpha by, sorry, just like this, say alpha by a minus gamma by c. Now I am making the group of this minus and plus. Alpha by a minus gamma by c divided by 1 plus beta by b. Previously we had plus and plus in both numerator and denominator, but we had just interchanging them. And over here 1 minus beta by b divided by alpha by a plus gamma by c. Okay, now we can consider this one as equal to mu. All right, so you can check that from these relations you will get a member of mu system. From these relations you will get a member of lambda system. So we can say that yes, through the point alpha, beta and gamma, we will have a member in the lambda system, generator in the lambda system, and a generator in the mu system. Okay, so these are the three properties that I was trying to mainly discuss. And the last property that I'm just not going to the proof of this property. It says that if you consider the point of intersection, and draw a tangent plane through this point of intersection of two surface of two generators. Say this is the point of intersection. Now if we draw a tangent plane, this type of tangent plane, in that case both of these two generators will lie on this tangent plane. If we draw a tangent plane at this point of intersection, okay, in that case both of these two, lambda system of generators and mu system of generators, will lie on this tangent plane. Okay, so we don't need the proof of this result. And the last result, and actually we have similar four results in case of generating lines of elliptic parabola. Now just briefly, within 2 minutes, I would simply draw the equation of this what we get, hyperbolic parabola, like this. So you see, this is the equation of hyperbolic parabola, this type of equation. X square by a square minus y square b square is equal to twice z. So this expression can be written like this: the left hand side, x by a plus y by b multiplied by x by a minus y by b, that is equal to twice z. and this twice z, this right hand side twice z, this can be written as equal to 2 multiplied by z. So we actually have two different factors over here. So we can combine this factor with this 2 and combine this factor with this z. And what we will get, you see, if you combine the first factor plus symbol x by a plus y by b with this first factor 2, you will get this type of relation. And if you combine x by a minus y by b is equal with this z, then you will get this type of relation. So together, both of these two equations will together construct a lambda system of generators. You can also make opposite type of combination. Say you can consider this plus factor, the first factor x by a plus y by b with this z. You can combine this one with this z and this second factor with this first factor. Then you will get another system of generator like this. This is called the new system of generators. And this would be actually the pictures. You see this type of straight lines, these are actually lambda system of generators. And if this is lambda system of generator, in that case this type of straight lines, okay, this type of straight lines would be actually new system of generators. So actually you can say that these are all lambda system of generators, and these are all new system of generators. So in this way, these generators are actually arranged, and all these four properties will hold good for lambda and new system of generators. Okay, so this much actually I wanted to discuss, and I also wanted to discuss two examples. Let me complete the remaining portion of the remaining discussion by considering one or two examples. Over here, what does it say? It says that find the equation of the generating lines of the hyperboloid x square by 4 plus y square by 9 minus z square by 16 is equal to 1, which will pass through this type of point. This is actually the point alpha, beta, and gamma. What I have discussed earlier, that through a point alpha, beta, and gamma, we can draw two system of generators. So we shall have to find out the equation of these two system of generators. And in fact, this is the curve that I have drawn over here. You can check the equation. This is the equation that I have drawn over here. This one, x square by a square plus y square by b square minus z square by c square. This is the curve that I have drawn, and this is actually the picture of this curve of the not curve, not actually, it should be the surface. So this is actually the picture of this surface. Okay, anyway, let's come back to this problem. So this can be solved by two different techniques. One is this kind of technique. So we consider a straight line, this type of straight line passing through the point 2, 3, minus 4. And what would be the equation of that straight line? X minus 2 by L, that is equal to y minus 3 by M. Over here it should be M, that is equal to Z plus 4 by N, that is equal to suppose R. Now we need to determine these values L, M, and N, so that this straight line will lie on the surface, and of course this straight line is passing through the point 2, 3, minus 4. Okay, so how to compute this value? You see, if you compare this first ratio with this last ratio, what you will get? X is equal to 2 plus L into R. So this is the first coordinate. You can check that this is the first coordinate, 2 plus L into R. Similarly, the y coordinate of a point on this straight line will have this type of expression, 3 plus m into r. The z coordinate will have the expression like minus 4 plus n into r. Now if this straight line, this equation number 1, given by this equation number 1 lies entirely on this surface, then all such points on the straight line, this type of points, all the points on the straight line must satisfy the equation of this surface. Okay, so we are just putting these expressions in this equation. We are just putting all these expressions, x is equal to this, y is equal to this, z is equal to this, on the equation of the surface. So we get this type of equation, and just making it simple, we get this type of equation. Some equation involving r square twice r, and as because all the points for all the values of r, small r, as because all the points for all the values of this small r will lie on this surface, therefore the final resultant relation involving r, this resultant relation, this is the relation, this final resultant relation involving r, this relation must be true for all possible values of r. Theoretically, r may vary from minus infinity to infinity. So if it is true for all possible values of r, therefore we can say that this would be an identity. Okay, and if it is an identity, in that case this coefficient of r square and this coefficient of twice r, both of these two coefficients must be identically 0. This must be is equal to 0, this must be is equal to 0. Otherwise it is not possible to make this left hand side 0 for all values of r. So this expression must be is equal to 0. This factor should also be equal to 0. So we get this type of relation. This is the first factor equal to 0, the first coefficient equal to 0, the coefficient of r square. Similarly, this is the second coefficient is equal to 0, the coefficient of this twice r. Okay. Now what we need to do, we can eliminate any one of these L, M and N. Over here in this book, they have eliminated this small n. They have eliminated this smallest small n from both of these two equations. After elimination this small n, what we get? We get this type of relation. And if we make it simple, we will get this type of relation. This 1 by 3 Lm is equal to 0. And it gives two results. Either L is equal to 0 or M is equal to 0. So if we put L is equal to 0 over here, for example, if we put L is equal to 0 over here, then what we get? You get M by 3 plus N by 4, this type of result. M by 3 plus N by 4 is equal to 0. And from this result, you can check that M divided by 3 would be is equal to N divided by minus 4. So what we get, if we L is equal to 0, then we get this type of relation. So we can say that M by 3 is equal to N by 4, and that is equal to L by 0. So what are the possible values of M, N and L? 3, M is equal to 3, N is equal to minus 4 and L is equal to 0. These are the three possible values of L, M and N. Similarly, if M is equal to 0, we can again compute the values of L and N. We can write L by 1 is equal to N by minus 2. So what we get? L by 1, that is equal to N by minus 2, and that would be is equal to M divided by 0. So we had this type of relations, L by 0. So we actually have two possible values of L and N. One value is L is equal to 1, M is equal to minus 2 and N is equal to 0. This is one set of value. And another set of value is L is equal to 0, M is equal to 3 and N is equal to minus 4. These are the possible two set of values. Therefore, if we put these values over here in this equation, if we put these values of L and N in this equation, you will get two generators. These are the two generators. These are the two generators. Therefore, in this fashion, you can compute these generators. So this is one technique, and you can also consider this type of expressions and find the values of lambda and mu, because you are given that this is actually passing through the point 2, 3, minus 4. So from this information, you can find the values of lambda and mu, and you can easily compute these two generators passing through the given point 2, 3, -4. Okay, so this is one example that I wanted to discuss, and another example, exactly similar type of example that I wanted to discuss is an example from this hyperbolic parabola. This is an equation of hyperbolic parabola, and we have to find out the locus of the point of intersection of the perpendicular generators of the hyperbolic parabola. That means the generators should be perpendicular to each other. Generators should be perpendicular to each other. Then we shall have to find out the locus of the point of intersection. How to find? You see, already I have discussed that this hyperbolic paraboloid have these two type of generators. One is lambda system, another is mu system. And if you solve these two equations, this is the first equation, this is the second equation, you can easily find out the direction ratio of this straight line. Say, let us call it the direction ratio is equal to L1, M1 and N1. Similarly, if you consider this second system, you can also find out the direction ratio of this mu system. Let us call it L2, M2 and N2. Now, as per the question, these two must be perpendicular to each other. Therefore, what is the condition of perpendicularity of two straight lines? That L1, L2 plus M1, M2 plus N1, N2 must be is equal to 0. So applying this condition of perpendicularity, you can easily compute the corresponding. You see, this is the condition. You can easily compute this type of relation. Okay, this type of relation. Now this is a relation involving mu and lambda. So now if you put the expression of lambda and mu from which relation? Already we have the expression of lambda and mu over here in this equation number 1 and 2. So if you just put the expression of lambda and mu from equation number 1 and 2 in this final expression, where is that expression? In this final expression, okay, you will get the corresponding required relation. So this is the locus of the point of intersection of the perpendicular generators of the hyperbolic parabola. So in this way you can find out the corresponding locus. So that's all for this lecture. Thank you for being with us.